There we go. I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Thank you for these students. And I just ask you to bless this class, Lord. In your name I pray. Amen. Let's see here. 5-5. All right, so last time we defined some things, right? In particular, we defined, let me just get it right up here at the start, definition, let K over F be finite extension right? Then K is Galois over F if what is true? If the degree of the F fixing automorphisms is equal to the degree of the extension of K over F. I should say the order of this group over here we have dimension of K as F vector space, right? So here we're, something in between theory of groups and theory of vector spaces, both working together to say something interesting about polynomial equations. And so K over F is Galois. Then in this case, in this context, we say that the Galois group of K over F is ought K over F. Wanted to follow up some of my waffling comments last time. Let's see here. I have the following notation, and I think I used this notation correctly last time, so I got lucky. All right, but just want to mention this. And this notation doesn't seem to be in Dummett and Foote, but it is in from Conrad blurbs. In particular, yeah. Oh, from Conrad's blurbs. So I'll write in black. Then L. You're like, I needed the red to be bigger. I don't care about the black. Let's see here. L upper H. What my larger point is what I've written in red doesn't matter. LH is alpha, but I hear you. I'll try not to do that. And I appreciate your comment. Alpha, an element of L, such that sigma of alpha is equal to alpha for all sigma in H. And so here we're looking at field L, and we're looking at H, a subgroup of the automorphisms of L. So this is the so-called fixed subfield of, how can I say this? The H fixed subfield of L, or the fixed field of H, all right, in the automorphisms. Well, yeah. Anyway, that's the so-called fixed field, all right. And so Conrad makes a couple of observations. One is that if we have a subfield f of L, all right, then f is a subset of the fixed fields, the fixed field of the automorphisms so aught L over F is the set of automorphisms, the F fixing automorphisms, all right? And this is saying that F is a subfield of its fixed field with respect to the field fixing automorphisms. Anyway, here it is. And also, H is a subset of the automorphisms of L, which fix the fixed field of H. This is also true. In this notation, one of the things I said last time can be restated as if H is a subgroup of H prime, then that implies that the fixed field of H prime is a subfield of the fixed field of H. That was that reversion, inclusion reversing statement I made last time. All right, great. So what I want to do now is I want to look at the example that that I glossed over last time. I want to actually start to sort through the details of that a little bit this time. It's one thing I want to do. All right. So that example that I started to look at but didn't really quite do justice to was from 14.1, example 5, the splitting field of x cubed minus 2. All right, so I'll try to go somewhat fast through this. Splitting field of x cubed minus 2. All right, so we know what the splitting field of this is. Let's call it K. It's Q. Adjoin, well, the cube root of 2. And also what he calls rho, where rho is, well, he also calls it zeta 3, also known as exponential of 2 pi I over 3. Right, so it's the primitive third root of unity. Okay. And so I'd like to calculate the, what have I done? Okay. I mean, there could be, you don't know what I did horrible things earlier today. If this lecture is even partially, if even somewhat decent, it'll be a miracle. So the, I want to describe, determine, whatever you want to say, the form of the automorphisms of K which fix Q, right? But as we discussed, that's just the automorphisms of K, right? And so to describe if sigma is a mapping from K to K, you know, and it's an automorphism, then we can pin it down, right, by what it does to, and instead of using sigma here, let me use something else like, I don't know, let's call it gamma for a second. All right. So to describe what gamma does, right, you think about it, you've got gamma, you have the cube root of 2, right? and you got to say what that goes to. And you got gamma and rho. You got to say what that goes to. Right? Yep.
How do you know that the automorphisms of k that fix Q are the same as just k?
Because we proved that any automorphism automatically fixes the prime subfield.
Oh.
Yeah. So this has to be an element, and this has to be an element of, I mean, you got to pick it, right? I mean, it's either the cube root of 2, it's rho times the cube root of 2, it's rho squared times the cube root of 2. I mean, them's your choices. All right. On the other hand, rho has to be sent to either, well, rho or what else? Am I doing this right? Sorry. Rho or any automorphism maps each of these two elements to one of the roots Oh, I haven't said this correctly. I'm sorry. That's not right. I was supposed to put, I wanted to put that here. I'm so sorry. Notice my correction. Yeah. Yeah. Yeah, I know what you're saying. That is a cube root of 2, yes. So, so basically, also, is this big enough? Sorry. Rho, I think what I'm, so I shouldn't use red. That's what I'm basically here. So here, so both of those have to map, right? Each one of those, in principle, you have rho times the cube root of 2 maps to either root 2, cube root of 2, rho times the cube root of 2, or rho squared times the cube root of 2. And likewise, either cube root of 2 maps to the cube root of 2, or it maps to rho. I mean, if you think about that, how many possibilities are there? How many maps, if you just think about just the raw possible ways to map two different, I mean, there can be, well, he says that there's 9 possibilities, all right? Just thinking about it. But that's, of those 9 possibilities, there's really only the ones worth looking at. Let me get to the point eventually here. It suffices to consider sigma. And sigma, what's sigma going to be defined by? Sigma, here's his notation for it. So this is just a nice notation for case-wise. So he says it's defined by the cube root of 2 maps to rho cube root of 2, and also rho maps to rho. That's our sigma. And the tau map is similarly defined to fix the cube root of 2 but rho, it maps to rho squared. By the way, rho squared is equal to -1 minus rho. This is not surprising. If you graph 1 rho and rho squared, right, on the unit circle, you can easily see that 1 plus rho squared is 0. Because the center of these 3 vectors is the origin. Yeah.
In the part for k equals q join those things, there it's rho times cube root 2, but then why is it not that later in like when you're defining sigma and tau? Then it's just rho?
I'm not sure I understand your question. So this splitting field is defined by rational linear combinations of these two elements and their powers. It's a degree 6 extension. And so to define an automorphism on it, it suffices to say where those generators go. So I've told you that this goes to that, and that goes to that. And have I made a typo? I mean, this, let's see here. So,
I think I'm confused because it seems like rho isn't a generator at the top, but then underneath it's treated like it is.
right.
But we still have, because sigma and tau are automorphisms, we do still
I mean,
have a definition, right, for what it does to.
Yeah, well, there are other ways to present K, right? I mean, if I take the ratio, right? If I take this guy divided by that guy, I get rho, right? So definitely rho is an element of K. So Q adjoin rho is a subfield of K. Conversely, if I had the third root of 2 and rho, I can get that. So I think they're just I mean, I think you could also just as well have written what I wrote originally. And I think that's what we wrote before, right? I don't think that's wrong. I mean, so the reason who cares? I mean, I care, but I think the reason he's looking at this is because these are, how to say this? I was trying to be able to follow what he says about there being 9 possibilities. I don't know. I mean, I guess whether or not you can, there aren't actually 9 possibilities. I mean, it turns out there are actually 6 distinct automorphisms to be found here, right? So if you think too hard about your quote-unquote possibilities, you'll rule out 3 of them early on. So to say there's 9 possibilities, you have to suspend your understanding of certain things. Otherwise, as soon as you count it as a possibility, you rule it out because it's not actually a possibility. So I think my stupid explanation at the moment is that by writing it this way, you don't have to suspend disbelief. I mean, you could in principle think there be 9 possibilities because you have 2 elements of order 3. They have to map to another element of order, well, not order 3, but it's an element such that it cubes to 2, right? So you have to, these, yeah, well, this and this certainly both cube to 2. And let's go on. This is not productive what I'm getting into at the moment. So these 2 are automorphisms. I mean, these define automorphisms. And specifically, we could, I'm trying to think, what is a general element? Well, I mean, fine. So really, I prefer to look at it that way, I guess. If I pick Z, or let's say alpha, if I pick alpha in the K here, then alpha equals to what? What's it look like? Yeah. Uh-huh. Let's stick with that. C.
plus the row cube root of 2.
Well, we could, I mean, yeah, now it's a question of ordering, right? Cube root of 2 squared, right? And then plus d row plus e row cube root of 2 plus f row cube root of 2 squared. I think that format, that choice of basis is probably most clear for understanding sigma and tau. Right? Because if you look at sigma of alpha, what's that mean? Let me write out what this notation is a superior notation to what I'm using at the moment, right? Like this really captures the meaning of sigma, but what that means if we look at an arbitrary element is sigma of alpha is actually going to be what? Well, a is fixed, and we get what? Plus b row root 3, 2 plus c row squared times the cube root of 2 squared. Wait a minute. Yes. So sigma of cube root of 2 is row root 2, but I get 2 of them, so I square it, and it gets back to this, right? And then d row is just d row, because row is fixed. And then e row cube root of 2, f row cube root of 2 squared. Grief. So what's going... Let's see here how to say this. All right. So what I'm trying to think about right now, foolishly, is if we ask the question. So think about H equal to the subgroup generated by sigma, right? So what happens when we square sigma? What's sigma squared look like? So if I, it maps to what? Whatever. So you're saying that's equal to row
Oh, no, sorry, yeah.
cube root of 2? Yeah. So row squared cube root of 2. And of course, row goes to row. And then if we calculate sigma cubed, focusing our attention on a generator's, focusing our attention on generators because we don't want to do this, right? This way of denoting it is very cumbersome. Yeah? I mean, that is the full-blown definition of sigma, great. You know, but from this, it's easy to see sigma cubed is what? What happens when you hit sigma on this? You get rho, 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 cube root of 2, otherwise known as boat, cube root of 2. Sorry, it's horrible. It's really horrible. Here's another row. Row goes to row. Of course, you can see that the cube of sigma is the identity map, right? So if I look at the subgroup of the automorphism group, right? Each one of these is an automorphism. So H is really it's got the identity, it's got sigma squared. What's the fixed field? If we ask the question, what's the fixed field? What's KH? What's the fixed field here? What subfield of the splitting field K here, right, is fixed by the automorphisms in H? Q adjoin rho. We have a winner, yes. Because no matter which automorphism in the subgroup H you hit rho with, it doesn't go anywhere. And so the field generated by rho, which is Q adjoin rho, is the fixed field. Anything, if it's got anything else in it, like a cube root of 2, well, that gets moved, right? Not by the identity, of course, but either by sigma, well, by both sigma and sigma squared, yeah? Okay, and then tau, well, what's tau squared look like? Well, I'll do the easy part. Cube root of 2 maps to the cube root of 2. Rho maps to what? Tau of rho, but tau of rho is rho squared, right? Because, I mean, tau of rho is rho squared, and that makes this tau rho, which is otherwise known as minus 1 minus rho times, what was tau of rho? Oh, it was rho squared, right?
Isn't rho cubed 1?
It is, and so, what do you want from me?
So it's rho to the 4th. So I think it should just be rho, right?
Oh, okay, so you're saying, look at this as tau of rho times tau of rho, which is rho squared times rho squared. And that's rho to the 4th, which is equal to rho again, because rho cubed is 1. Yeah, very good. So however you want to see it, tau squared is 1, right? And so we could look at another subgroup. Let's say this was H1. All right, let's call this one H2. H2, the subgroup generated by tau, subgroup of order 2, right? What is going on over there today? So we got our 1 and a tau. What's the fixed field of H2? Yeah, Q adjoin the cube root of 2. Now, continuing to work on here, he says, a non-example, so he says, you got to be careful So here's, let me call this a gamma. Let's say gamma is defined by sending the cube root of 2 to rho times the cube root of 2, and rho times the cube root of 2 to rho times the cube root of 2. Like in principle, he says you could do this, but he said that is not, what he says is some care must be exercised in determining Galois groups from its action on generators. As mentioned, not every map taking cube root of 2 and rho times the cube root of 2 to the roots of x cubed minus 2 gives rise to an automorphism of the field. For example, this takes roots of x cubed minus 2 to other roots of x cubed minus 2, but this is definitely not an automorphism. Why is this not an automorphism? Yeah, it's not injective. Right. In contrast, the sigma and tau that we just built are injective, right? They're surjective because they map to the generators. But there's more. They also have to respect, there's more that has to go on here, because there's a relation, right, that's, this relation here also has to be respected by these maps. You know? Can you see why that would be? Like, I mean, let's look at the interesting one. Well, why is tau of 1 plus rho squared? What's that equal to? Tau of 1 plus tau of rho, right? Plus tau of rho squared. So what happens there? Well, tau of 1 is 1. All right. Because we're assuming that much. Tau of rho, well, we define that to be rho squared, right? And what was tau of rho squared? We worked it out. It was rho, yeah. And that's 0. See, it didn't have to work out to be 0 in principle. Like, if you define how if you define how the generators map to generators, right, independent of some condition which is shared by the generators jointly, you also have to mind that condition that it be preserved by the automorphism that you think you're constructing. So I'm just saying there's a subtlety in constructing automorphisms which becomes more apparent in more complicated examples, but maybe not so much here. Yeah. Then the other question is, how do sigma and tau interact, right? And so he points out, and I don't want to use, I've probably already used all of class time, haven't I? Great. You can calculate that sigma tau is equal to tau sigma squared. And if you think through, it's easy enough to check that, right? I mean, you just follow the generators and see what happens. Like sigma tau, if we start with, root 2 and rho, we do the tau. What's tau do? It takes the rho to rho squared, right? It takes the cube root of 2 to cube root of 2, right? And then we do another tau, because we're doing tau squared, right? Cube root of 2, still cube root of 2.
Are we doing sigma?
I'm getting there. Oh, good grief. What have I done? I'm supposed to do... Yeah, like I said, thank you. Grief. So sigma fixes rho squared, doesn't it? Yeah. Yeah, wonderful. And then sigma maps that to rho times the cube root of 2, right? All right. And then we can go through the same thing for tau sigma squared. Start with the generators and see where they go. Where does sigma squared take rho and the cube root of 2? I mean, we have it over there. What's sigma squared do? Fixes rho. And it takes the cube root of 2 to rho. I think it takes it to rho squared. Or if you believe rho to the 23rd root of 2. That was a joke. Let's see here. Tau. What happens with the, then I do tau. What's tau do to rho? Changes it to rho squared, right? And what does tau do to rho squared times the cube root of 2? I don't know, you probably need to work through that, right? That's tau of rho squared times tau of the cube root of 2, which is what? Tau of rho is rho squared. Rho squared squared is rho to the 4th. Rho to the 4th is rho. Tau of the cube root of 2 is cube root of 2. So as you can see, both sigma tau and sigma tau squared produce the same action on the generators and therefore generate the same automorphism. Right? So this proves that this is true. All right? So if I was a linear algebra student, I'd take off half the credit because I wrote the thing I was trying to prove at the start and didn't say I was trying to do that. But, you know, don't tell them. Okay. There is a slight difference. I know what I'm trying to do, right? Even if I don't do it, I know what I'm trying to do. Okay. Great. So the larger point here is what? The Galois group of K over Q, if you like, is the it's the group generated by sigma and tau, right? Which in more detail would be something like, you know, well, I guess the typical notation we've used for this would be like sigma tau such that sigma cubed equals to tau squared equals to 1. And we've got this handy-dandy relation up here, sigma tau equals to tau sigma squared, which you might recognize more if I wrote that as sigma inverse, right? Because this is exactly up to isomorphism, the symmetric group on 3 things, right? This is S3, which has order 6, right? So I really shouldn't write gal just yet. What should I write here at this point? I should write ought. This is the Q-fixing automorphisms of K, but notice that the Q-fixing automorphisms of K has degree 6, and that is, of course, equal to the degree of the extension of K over Q, because we proved before that the splitting field of x cubed minus 2 over Q has degree 6, right? So therefore, this is a Galois extension. Right? And you can see that, in fact, I could have written that this is equal to the Galois group of K over Q. All right. So that brings us, slowly but surely, to the next section. Mostly slowly. Ah! No! Ah! Ah! The worst. Just the worst. What did I do that for? Of all the things to erase. You took notes. All right, well, that's good. So in section 14.2, he starts by discussing the, so here's, oh, come on. I'm forgetting something. So in 14.2, he starts with this discussion of what's called a character, and then he proves corollary 8, and then he uses that to get to Theorem 9, and Theorem 9's proof is 2 pages. And I'm just going to state Theorem 9 because actually I don't think that, I mean, if you look at the proof, it's rather accessible, it's not that bad, but really it's just linear algebra. But it's linear algebra on those characters. And my larger point here is I don't really think we're using those characters other places in here, so I'm not convinced it really is needed. I may regret it, but I seem to recall that skipping the proof of Theorem 9 is a good idea for lecture in here. Sigma n. I mean, I love the proof of Theorem 9. It's linear algebra. But anyway, if we have G is this the subset of automorphisms of K, okay? Aut K. And let F be the fixed field. So if F is the fixed field, what is our notation since we, see I just erased it, but if F is the fixed field of G, what would it be here? No. How about K? Upper G, I think. Right? All right, whatever.
I took notes, I promise.
G upper F? Yeah, no. All right, so. So that would be the fixed field. Or I could say a better way to say it perhaps would be the subfield of K fixed by G. There's a sentence which is true. All right? Then, here's the deal. The degree of K over F is equal to n, which, by the way, is the order of G. What does this mean in words? We put it into words here. So, in our other notation, K over the fixed field of G, right, is equal to n, which is equal to the degree of G. If we have the order of G, right, what was our definition of Galois? What would it take for K over F to be Galois.
Have to contain all of the automorphisms for that extension, for the extension of K over F.
Would G have to contain, what was your, what? Well, the other thing I should have done here, but obviously I'm out of time, is I should draw the picture of the lattice of this is my own stupid fault. I'm having a help session in here after you guys. Now they're, of course, assembling in the hallway making noise. All right. Which I should have anticipated. But on, oh, phooey. If you look at page 568, right, they have the picture of the Galois group and its subgroups, contrasted against the picture of the splitting field and the subfields of the splitting field there. All right, and you can see it's the same pattern if you invert the diagram. And that's what we're going to try to explain next class. I will eventually make progress in here. It seems like I didn't make any progress today whatsoever. Anyway, I shut up. Oh, did I top out you guys yet? Yeah. Okay. Yeah.